ahead and solve this differential equation to find the general solution. So that means we're still going to have our constant of integration, and we're not going to be given an initial value. So we have dy over dx equals 8y times the quantity 100 minus y. So this is pretty easily separated. So I'm going to move my y's over by dividing both sides by y times 100 minus y. And I'm going to move my dx over at the same time by multiplying both sides by dx. So the equation I have now is that dy over y times 100 minus y equals 8 dx. So I'm going to zoom in now so we can just focus on one thing at a time. And I'm going to fix the x because it's really awful looking. Okay, so once we have our variables separated, we can integrate both sides. So the right side is very easy to integrate, right? We're just integrating 8 and we're integrating with respect to x. So that's going to be 8x plus my constant integration. Now, when I go to the left side, right, I have a rational expression there and the denominator is factored. So that means that I'm going to have partial fractions. So I'm going to go off to the side to integrate this. So let's do this in a different color, go off to the side real fast. Okay, so if we have the integral of dy over 100, oops, missed the y times 100 minus y. I'm going to do partial fraction decomposition. So my numerator is 1, denominator is already factored, and that's going to equal my partial fractions of a over y plus b over 100 minus y. So if I solve to make the numerator one equation, right, make my common denominators, I'm going to get that 1 is equal to a times 100 minus y plus b times y. So now if I solve for a and b, I'm going to plug 0 in for y. It's going to give me 1 equals a times 100. Right, my b's are going to cancel out. Okay, so that's easy. A is equal to 1/100th. And if I plug in 100 for y, my a's will now cancel out. I'll get that 1 is equal to b times 100. Oh, super easy. They're the same. Right? So now, move that off to the side a little bit. If we take our integral, we can separate it to be, okay, this is 1 over 100 all over y plus 1 over 100 over 100 minus y dy. So when we go to integrate it, this one is very easy, right? I'm going to just kind of box in my integration by parts work so it's separated, right? That's super easy. That's just going to be, if my iPad will cooperate, 1/100th times the natural log of the absolute value of y. But when we go over here, because of this minus sign, if we were to do a quick u substitution here, right, if we made u equal to 100 minus y, my du here would be negative dy. So I would want to plug in a negative du equals to dy. So I'm not going to do the full integration with substitution there, but because of that negative du part, I'm going to get a negative in between my natural logs. Then I'm going to have 1 over 100 times the natural log of the 100 minus y, since that's in the denominator, right? And since I'm off to the side and this is an indefinite integral, I'm going to add my constant of integration. So when I zoom back out so we can see the whole problem now, I'm going to go ahead and take this stuff, right, and plug it in for the integral over here. But before I do that, let's just condense it a little bit so it's a little easier to write. So they both have a factor of 1/100th. So I'm going to take that out times the natural log, and because of the minus sign in between them, I can condense the natural log so it's y over 100 minus y, right, using our log properties. So I'm going to actually replace this over here. So my integral of dy over y times 100 minus y is just 1/100th times the natural log of the absolute value of y over 100 minus y. Okay, now let's just focus on this. So we want to solve for y. So I'm first going to multiply both sides by 100. Okay, so I get the natural log of the absolute value of y over 100 minus y is going to equal 800x plus c, right? Technically, those two c's are different. If you wanted to, you could label this as c1 and this is c2, right, where c2 is just 100 times c1. I don't really do that. Oh no. I just kind of let them be c's, and you solve for the c at the end anyway if you need to. Okay, so I want to rewrite this so there's no natural log, so I'm going to write it as an exponential. So this is going to be the absolute value of y over 100 minus y equals e raised to the power of 800x plus c. And then I'm going to use my exponent rules to break this apart, right? I can break that off as e to the 800x times e to the c power, right? That's the same thing here. And e to the c is just another constant. So once I bring down that e to the c as a new constant, I can actually get rid of my absolute values because that c value that's now in the front will take care of whether or not I need it to be the positive or the negative to take care of the absolute value if we were given an initial value to actually solve with. Okay, so now we need to solve for y. So I'm going to multiply both sides now by 100 minus y to get rid of that denominator. Okay, so now we have that y equals 100c e to the 800x minus y times c e to the 800x. And you're going to see why I didn't, 100 times c, you could definitely make it as another c value, but I'm just going to leave it alone because right now the two c's I have are the same value, and that way I don't have to label them with subscripts. Okay, so now I need to isolate y, so I need to move this to the other side. All right, I want all of my y's to be the same. So that gives me y plus y times c e to the 800x equals 100 c e to the 800x. It's a lot of algebra, I know. So now I can factor out a y here, which means I can finally isolate my y's, which is great because I want to solve for a y equals equation if possible, which it definitely is here. Right, and then I'm just going to divide both sides by that 1 plus c e to the 800x. Now, technically we're done, right? This is a general solution. It has the y equals part, it's all good that. But it's a little messy to look at, so let's combine all of the e's. Right? It would be really nice if I didn't have e to the 800x in two different spots, if I could kind of condense it. And we can do this, right? We can manipulate a fraction as long as we do the same thing to the numerator as we do in the denominator. So just hang in there with me. I know that, why is she doing this? It's for a specific reason. So what I'm going to do is I'm going to multiply the top and bottom of my fraction by 1 over c times e to the negative 800x. Right, and technically I'm going to distribute that through the denominator. Okay, so when I do that, right, the c here and the 1 over c here are going to cancel, and then e to the 800x times e to the negative 800x is e to the 0 power, which is just 1. So I'm just left with 100 in my numerator, so that looks a lot nicer already. And then when I multiply this through in the denominator, I'm going to get c times e to the negative 800x plus, right, my c's here are going to cancel out when I multiply, and my e's are also going to cancel out, so plus 1. So that green c there, right, when I do 1 times my 1 over c e to the negative 800x, 1 over c is just a different constant, and now it's my only constant, so I'm just still going to label it as c. So all I'm going to do now is write it so the denominator is flipped. And the reason I'm going to do that is because, well, this video is titled the Logistic Growth Model. This is a logistic growth model curve. This is an example of one. So you actually just solved a logistic growth model differential equation without even knowing what it is. Now, this was a lot of algebra, right? If I zoom out, look at all that algebra that we did just to solve that one equation, right? That was a lot of work. So we needed partial fractions to solve a logistic growth equation. That's actually one of the reasons why we learn about partial fractions. Not just that it's like a super cool integration method to use and it works really great for rational functions. You need it in order to talk about logistic growth. So now that we've solved the differential equation all the way through, I'm going to give you the formula so that way you never have to do all of this algebra again on your own. So now you know you can if you forget the model, but if you memorize the model, it's a lot faster. So we know about two different types of growth models. Well, you know about one, I'm about to teach you about the other. So the first type of growth model that we've talked about, and a lot of our differential equations turn out being this, is called that direct proportional growth. So that's what happens when our dy dx equation looks like something like k times y, a constant times the dependent variable. Right? So what this model says is that the growth over time is unlimited. Right? And we use exponential growth to talk about a lot of things. We talk about bacteria populations, half-life, right? A lot of times, especially like if you think back to like exponential growth and decay, when we learned that in Algebra 2, you talk a lot about populations of people. But if you think about it, population growth can't be exponential truly, because you can't support an infinite number of people, right? If you look at the graph of the model, right, we know that our model here is equal to, if we solve it, y equals c times e to the kt, right, where c is the initial value, right? We know that if we draw a graph of that, our curve looks like this, right? The limit as t goes to infinity of our equation, c e to the kt, that equals infinity. So if you're using this as a growth model for population, right? Say we're in Pennsylvania, right? Pennsylvania can't support an infinite number of people. There's a limited amount of resources and space and like food and water and all of that good stuff. So in other words, there's something called a carrying capacity, and that's where the logistic growth model comes in. So the logistic growth model looks a lot like what we started the last problem with. So dy dx is equal to k times y times, so it's almost exactly the same as direct proportional, but we add in this extra piece, L minus y. Right, so we still have this like directly proportional growth. But now we've added in this extra quantity, and this acts as a limiting factor. Right? So you're saying that as time goes on, right, you're doing L minus y, so that means your y can't go over your L value. So L is what we call the carrying capacity of the system. Right? So if you're talking about a system like even a school system, like say a rumor is spreading at a certain rate, right? If there's only 1,200 students in the school, you can't tell the rumor to more than 1,200 people. There's a limit on how many people you could tell that rumor to, which one, you shouldn't gossip because that's rude. But two, right, there's only so many people you could tell if you were going to spread a rumor, right? So the carrying capacity is kind of the largest amount of people that it can support, right? The system can only support so much growth, right? The system can only support growth to a certain amount. Right? Just like if you look at a school building, right, our school can only hold so many people. So the population growth of our student body has a limiting factor because it's the amount of kids that we can put into a classroom at any given time. So the model for this one looks a lot like what we just solved for. I'm going to give you a little mnemonic device to help you remember it. It's going to look like y equals L over 1 plus c e to the negative lkt. So the little mnemonic device that we're going to use to help us remember this is lice minus lict. And the reason that helps us remember it is, right, lice, L-I-C-E, right, so that's L over 1 plus c times e, and then minus licked is that negative L kt exponent. Right, so if we look at that model real quickly, if we go back to what we just solved for, y equals L over 1 plus CE to the negative LKT, we can see here that our L is 100, right? Our limiting capacity is 100, and our K value is going to be equal to 8. And we can also tell that based on the initial value, right? This is our K, this is our L. Right, so this is a logistic growth model. That's why I solved it to look like this, so it totally matches the model I wanted to talk to you about. So what the graph of this model looks like is you have this limiting capacity at L. So you have a horizontal asymptote. Right, so our model looks more like this. There's eventually an inflection point where the population is still growing, but it is growing at a decreasing rate because you're getting closer to the limiting capacity. So in other words, if we take the limit of a logistic growth model, right, we can see that we're going to approach that limiting capacity. So we no longer have infinite growth. So last thing I'm going to do in this video is we're going to kind of go back to that first differential equation model that we solved, and we're going to analyze that using a little bit more of this logistic growth information. So we're going to use the model from the first example, just said that. When is the quantity y growing the fastest? So if we want to know when y is growing the fastest, we want to know what is the maximum of dy dx, right? We want to know when is it growing the fastest, so what's the maximum growth of the rate of change? Well, that's the maximum of the first derivative. So what we want to do is actually take the second derivative. And so this is going to be implicit differentiation because we want to take it with respect to the independent variable of both sides. So I'm going to show my implicit differentiation, show what I'm taking the derivative with respect to, right? So that way anyone who's grading my work or looking at my work knows exactly what I'm doing. Okay, so the left side comes d squared y over dx squared, right, our second derivative notation. And now I'm going to have to use product rule. So the derivative of my first part is going to be 8 dy dx, right, times my second group, so 100 minus y. And then I'm going to do plus the derivative of my second group. So the derivative of that is negative dy dx, right, times my first group again, so 8y. So I'm going to go through, and everywhere I see my dy dx's, I'm going to replace that with my dy dx equation. So my second derivative is going to equal 8 times 8y times 100 minus y, all times 100 minus y, minus 8y times 100 minus y, plugging in my dy dx, all times 8y. Okay, so if I simplify a little bit, I'm not going to fully multiply through, but we can combine things, right? So 8 times 8 is 64y in the front, and then I have 2 of those 100 minus y groups there, and 8y times 8y is 64y squared times 100 minus y. So now this equation I can actually factor because it has a GCF, right? Both parts of the equation have 64y and a group of 100 minus y. So I'm going to go ahead, leave that in this color, and factor that out. So when I factor that out, the first term is going to leave me with one of those 100 minus y groups. And the other one is going to leave me, I take out the 64, I take out one of the y's, I have one y left over, and I took out the group of 100 minus y. So overall, my second derivative is 64y times 100 minus y times 100 minus 2y if I combine those two negative y's in there. So now we want to remember, why did we take the second derivative? We're trying to maximize the first derivative. So I need to set this equal to 0. Now, since I already have it factored, I know that I'm just going to set each part equal to 0. So this one's really easy. Y is 0, Y is 100, and Y is 50. So now I'm going to make a little sign chart. So I have a 0, a 50, and a 100. And I know my second derivative is equal to 0 there. So now before we start plugging in values between each of them, right, the limiting factor of the system, the L value is 100, which means that I'm never going over 100. So I don't even have to bother testing that part of it. Okay, if I plug in a number to the left of 0, if I look back at my factored form, I'm going to get a negative number times a positive, so this is going to be negative. Right. You can go ahead and use your calculator. Say I want to plug in 25 and 75, right? You can go ahead and pause the video and plug those in on your own. But if I plug in 25, I'm going to actually get a positive value in between. And then if I plug in a 75, I'm going to get a negative value because the first two factors are going to stay positive, the last one will go negative. So that means I have a maximum happening at y equaling 50. Right, so the quantity y is growing the fastest when y equals 50. Now notice what 50 is, right? 50 was half of the carrying capacity. Right, that was 100 over 2. And that's actually a really important pattern to look at. So the quantity is always going to be growing the fastest. The inflection point always happens at the L over 2. So I'm actually going to go back to our notes about the logistic growth model, right? And that's really important. The inflection point always happens at L over 2. Always happens at L over 2. And this is when y is growing the fastest.